to train object detection models on TensorFlow. She is a student from India and machine learning engineer at IonCure startup. Hello, Nigama. I think you are muted.
Hello, can you hear me now?
Yes, now we can hear you.
Okay,
So yeah, you can start sharing your screen and you can start with your talk.
Okay, great. Just a second. Are you able to look at my screen?
Yeah, we can see it.
Okay. Hello, everyone. Thank you so much for joining the session. I'm Nigama. Before we start, a little bit about myself. I'm a sophomore student studying in India. I also work part-time as a machine learning engineer in an early stage startup called IonCure. So today I'm going to be talking about how object detection works, how to build an object detection model, and I'll also discuss a use case of object detection that I worked on, which is a sign language detection model using TensorFlow. I'll walk you through my approach of building the model, how I used transfer learning and all of this stuff. And then finally, I'll discuss about how I'm planning to improve this model so that it can be used by people in real time. So yeah, let's get started. First up, a little bit about object detection. Object detection basically involves picking a bounding box around the object of interest in some images. And object detection is used almost everywhere these days. It is used to detect humans, it is used to detect things and objects. And even when a Tesla car is driving by itself on the road, it detects objects around it, and that is how it is able to move through the space. So yeah, I just wanted to say that object detection has become a very powerful tool lately. So if we want to build an object detection model, there are some basic deep learning concepts that we need to understand first. We need to understand how CNNs work. We need to understand how RCNNs work. We also need to know how to use the popular TensorFlow object detection API. So let's start with understanding CNNs, which stand for convolutional neural network. To start with, when you're working with a CNN, you have some input data. You're going to do some convolutions, and that generally is just creating feature maps, and we'll talk about those in just a little bit. And then we do some pooling. Usually it is called max pooling, and I will also explain about this too later on. And each of these you do is going to be a hidden layer. And then generally you will add one fully connected layer, which would also be a hidden layer as well. And finally, you have your output. So a fully connected layer is usually something that takes the end result from a convolution and pooling and comes to a classification decision. So it is basically connected to the output layer. So when you do a convolution, this is generally any form of mapping or creating a feature map from an original data set. And what this is going to involve is just going to be this moving region or this moving window over your image that is looking for something or is going to create a feature out of a window of pixels. So sometimes you might have this searching through an image, looking for either horizontal or vertical lines or edges and so on. And therefore you use a library such as OpenCV for this purpose. To visualize this, let's take an image. Let's assume we have an image of a cat and it is divided into pixels. So whenever we pass this image as an input into the CNN, it is broken down into small pixels like this. So Each of these squares is a pixel. And for example, if we do a 3 by 3 convolution, we might start with a window which looks like this. And this new window is going to pretend as a new cell. And then we shift that 2 spots over. And this continues until the window slides over each and every pixel of the image. So now we move this window down to the left. So the 3 by 3 convolution is over here. And finally, the last 3 by 3 convolution will be over here. So this process continues until it doesn't skip any pixels from our input. And that is how convolution works. And of course, this is a very simplified version of how it works. So if this is convolution, then what is pooling? Let's say you've done all this convolution and it has just produced some values for us. So again, we created these new kind of boxes, or each of these new kind of regions from the image, and they might actually have values in them like 2, 3, 4, 1, and so on. So let's say these are new feature map with values, and now what we're going to do is we're going to do some pooling. Again, to keep it simple, let's do a 3 by 3 pooling. So when we pool, it is a little bit different from when we created the feature map. When we created the feature map, we created what pooling is actually going to do for us, but we kind of also extracted those values. Now, when we're taking 3 by 3 pooling, it is usually called max pooling, and this is because we are looking for a maximum value in this particular window, and that maximum value here is a 4, right? So when we shift it over the next, and then we have this box, and then the maximum value over here is a 3, and then we come down, the maximum value is a 4, and then here again, and the maximum value here is a 3. So again, this is an extremely simplified version of what pooling does, but that is kind of the idea behind it. So this convolution and pooling together gives us what is called a hidden layer. And you will usually have 2 or more hidden layers. And then finally, it is connected to a fully connected layer, which is basically something that collects the output from the hidden layers. And then we have our final output. So this is the idea behind how CNNs work. So now we know for a fact that convolutional neural networks can help us in identifying images, right? But the real world is much more complex than images, right? So when we humans look at our surroundings, we can identify what objects are present around us in a matter of seconds. So not only our mind can identify them, but also we can see how different one object is from the other. Now the question is, can convolutional neural networks do this task? The answer is yes. And the way they do that is, let's say we take an already existing convolutional net like VG16, and we want to kind of repurpose it for object detection. But how do we do that? So basically, to achieve that, we take an existing classifier or an existing architecture like InceptionNet or VGG16 and other architectures, and we take our image that we want to give as an input. And let's say we want to detect for any, just a second. Let's say we want to detect for a motorcycle in this image. Now, the pre-trained models can obviously detect a motorcycle in this image because these are huge neural networks that has been trained on tons and tons of data set. So Now, what we can do is sort of take this pre-trained model and slide it over our target image. And if you remember how CNNs work from what we discussed earlier, when we pass the classifier through every window of that image, it is going to classify as many objects as possible from that image. So we basically end up with a huge number of classifications, amongst which our target object, that is a motorcycle, is one of them. So there has to be a better way of doing this. Instead of going through each and every window and instead of going through each and every window, we have to have a better approach for this. And that better approach was proposed very recently, and that method is called RCNNs. Now, what RCNNs do is instead of working on a massive number of regions, the RCNN algorithm proposes a bunch of boxes in the image and checks if any of these boxes contain any object. And RCNN uses something called selective search to extract these boxes from an image. So basically, in selective search, there are various regions from an object, and it classifies the images based on features like colors, textures, enclosures, and so on. And when these patterns or features are identified, it proposes various regions from the image. So let's say this is, it takes this image as an input. Then it generates initial subsegmentations so that we have multiple regions from an image like this one. And then this technique, this selective search technique combines all of these similar regions based on these different features that we talked about and forms a larger region and finally produce object locations. So this is how RCNNs are different from CNNs. Now, coming back to utilizing these models, why do we concentrate on using TensorFlow particularly? The reason why this is so kind of useful or powerful is detecting things in images is something that has been existed for a very long time. But detecting objects in images that you could stream kind of like on a video and to detect things at 15 to 20 frames per second, and especially if you want with a decent accuracy. Now that was a big challenge, and to write the code from scratch by yourself that is going to do all of this for you would just take forever. So this TensorFlow API does most of the work for us since they already have large number of pre-trained models. Now, I want to share a use case that I worked on, which is a sign language detection model to basically improve my understanding of building deep learning models. So the main objective of this was to use the TensorFlow object detection API and train the dataset to detect these different images and convert them into text. And I specifically focused on American Sign Language because they have a really active online forum, which was really important for me to derive the dataset from. Before that, I want to talk a bit about sign language processing. Uh, so there is a misconception about sign language that there exists only one form of sign language, and that is not true. Every country has its own form of sign language, like German Sign Language, British Sign Language, and so on. And yeah, it basically depends on the geographical location, right? So here I started out with a goal to translate the entire sign language, and it was actually a bit much. And I had to narrow down my scope and really focus on a few different signs at a time. Like, for example, I trained my model on signs which represent basic signs such as hello, yes, no, and yeah, so I basically concentrated only on these basic signs. And so, like most machine learning and deep learning systems, we start with collecting the data set. I initially thought I would just use the data that is available on the internet from online forums or Kaggle, but I was not really satisfied with the results that I got. So I decided to make my own dataset with the help of OpenCV, Label Image, and Python. And then after data collection, we do some pre-processing, feature extraction, and finally we get a real-time system. As discussed earlier, I focused using CNNs for pre-processing and feature extraction, and specifically some transfer learning as well. Since I'm using my own dataset, it was to use that dataset, it was very limiting to use that in a real-time system. So how does this all work together is first up, we use our own webcam to collect images that we are going to use to train on. And those images are then going to be passed to label image, and we start drawing detection boxes against these different sign language poses. And once that is done, we can use transfer learning against the TensorFlow object detection API to be able to train on train on an object detector. And the last step is to use Python and OpenCV to detect those different sign language poses. And OpenCV really makes it simple with its video capture object. So it basically connects to your webcam and lets you read in frame by frame and apply whatever the operations that you need. And ideally, what we end up with is a real-time object detection device that uses your webcam to identify these different sign language poses. Now, I did talk about transfer learning earlier. I want to talk a bit more about it. I think it is one of the most powerful ideas in deep learning. And this is because sometimes you take the knowledge that a neural network has learned before from one task and apply that knowledge to a different task. So, for example, a neural network has learned to recognize a cat or a dog. We can use the power of that knowledge and apply to our own models, our custom models. And for example, architectures like MobileNet SSD, which is a predefined model, which is also offered by TensorFlow, is used as the base and this fine-tuned and is also fine-tuned to improve the accuracy and the range of the objects that can be detected. And this model can be trained for any custom object that is required by the user to keep track of that particular object. So now, the ultimate goal of this project was to develop a real-time sign language detection application that will be accessible for everyone, but the existing video conferencing apps like Skype or Zoom or Teams only detect speakers by voice activation. So it is really a challenge to identify if someone is signing at any given moment. And this is the reason I wanted to develop an application that is fast and still reliable. So to improve this further, I had this option to basically convert this model into a TensorFlow JS format to run in the browser. Now, TensorFlow JS model is again basically a JavaScript library for training and deploying machine learning models on the browser and also on Node.js. But why would someone want to run their object detection model locally on their browser, right? So the idea of doing it locally in the browser is that you can get a lot higher speed so that you can do it in real time instead of having to wait for those API calls to go through and stuff like that. And it is also the kind of the concept of AI on edge versus AI on cloud. So when we convert that model into a TFJS friendly format, we can then use that to make real-time detections using React.js and our webcam and our own webcam. And finally, we can also visualize these real-time detections on the screen, and now you have your own model which can identify various sign language poses. Now, the cool thing about this is you can use this exact same format and the code that you used here and apply it on any other use case that you want. Like if you want to detect vehicles, if you want to detect stop signs, for example, and a whole heap of other applications as well. So yeah, uh, I will leave a link for my GitHub repo on the resources page. I'll make sure other links are updated as well so that you can read and build your own object detection models. So yeah, that's all about it. Hope you learned something from my session. Thank you so much for listening, guys.
That was great, Nagama. Thank you so much for sharing. What an amazing project that you worked on there. Thank you. Yeah, really, really, really interesting. We do have a couple of questions for you. So the first one is from our audience. So let me just, here we go. So which object detection model is fastest in your experience? YOLO, fast RCNNs. Have you compared different models for sign language detection?
Yes, so personally, I think YOLO is very recent, and I think it was proposed like in 2015. I don't know, I'm not sure, but I think that's the more advanced one after RCNNs. Yeah, because YOLO, the concept of YOLO is basically you only look once. It only looks once at an image, and it can basically classify it. So I think YOLO is the best one to go for.
Fantastic. Good advice. Good advice. And there's a follow-on question from that. So how many object classes did you train for?
In what context?
So I think you have lots of different words from the sign language. Was there a certain amount of classes that you were looking for in your transfer learning, or was it something broader than that?
Yeah, I was just concentrating on fewer words, fewer phrases, like not alphabets particularly, but phrases of words like hello, total words.
Great.
I basically pass them into label image and mention them as hello, I love you, or other phrases like that. Yeah.
That's cool.
I basically trained only on five phrases, I guess, yeah, because I wanted to keep it accurate and I wanted to be accurate, so
yeah.
Yeah.
Yeah, no, that's really interesting. I guess these kinds of models, as you're training and experimenting with them, if you start with the smaller amount of classes and then gradually add to them, and hopefully start to see scale. But if you start to lose accuracy, obviously that can happen if you have a lot of different classes or classes that are quite similar. You spot that rather than just throwing them all in there. So that's a really, really cool approach. I have a question for you, actually. You explained CNNs and RCNNs really very succinctly, very well, very efficiently. Where did you learn about CNNs, the theory of it? Did you learn that for yourself? Was that on your course that you're on?
Yeah, so everything that I learned about AI or coding, everything was off of internet from YouTube and all those resources. I didn't take any courses, so everything
Wow.
is off of internet. So yeah.
That's fantastic. I mean, congratulations. That's really, really impressive. And you just kind of went out and found them. There is so much out there, isn't there? We heard from a career panel, a unit like should you go to university or not to learn AI and deep learning, and that kept coming up that it was theory is good to make sure you go understand, and a lot of things are now available online for everyone to take advantage of. So it's great to hear that you use them. You, what do you mind me asking? What's your background? Because you've done a really broad project there. Like it was, I feel like you epitomize the word data scientist because you were like, I had to go and research that it was ASL that I was looking at, and I needed the forum of people to get their insight and their advice, and then the pre-process, and then finally the machine learning model, and also where you were going to put it. You mentioned all the different types of models, whether it was on the device or in the cloud, etc. Was that just different parts that you learned yourself, or did you work with a team?
No, I did not work with a team. This was just my project that I started like 2 months ago. It was just for me to understand how deep learning models work, how I can implement them. So this was one idea that I implemented amongst many. So yeah.
Love that. Well, congratulations. It's an incredibly interesting project. You're getting lots of praise in the chat, so do go to the website and check that out as well. People are really enjoying the project that you just explained, and if you have any resources, we will put them onto the resources tab for you so that we can share them. That's great stuff. So just before you go, actually, what would you recommend as everyone's next step here to maybe build something similar?
So I wouldn't say everyone to build exactly what I built. I would suggest everyone to have a goal in mind, the end goal, what you want, the product, what you want to create, and kind of work backwards. Like after you learn all the basics and all of that stuff, there is a very high chance that someone else already has your idea and they have already made it. So search for it, dig the internet, and work your way backwards to building your product. Yeah.
Fantastic. Thank you so much for your time, Nagana. It is an absolute pleasure to have you on and talk about object detection. No problem. Using TensorFlow. For those out there who haven't used TensorFlow before, you can also do object detection in Azure Custom Vision, which brings us nicely onto our next topic. Before that, I just want to reiterate that we have our Cloud Skills Challenge available. So if you go to aka.ms/AI/challenge, you will be able to go ahead and take part in that. You have the opportunity to win a swag bag if you become part of the top leaderboard, and you also remember you have a full week to complete those modules, so get signed up to